We're going to go ahead and take a look at more complicated rational functions today, and we're going to discuss the different types of asymptotes that you can find according to the type of function you're working with. So, first of all, let's go ahead and review what we learned in yesterday's lesson. Given the rational function of f of x equals 1 over x minus 2 plus 3, we know that we can identify the domain based off of our h value. Okay, so in this case, our h is equal to positive 2, so we know that the domain is everything except for positive 2. And the reason for this is because it is undefined at x equals 2. Remember, this comes from our h value. Okay, now based on the graph of this function, we also know that it has a vertical asymptote at x equals 2. All right, our vertical asymptote comes from the domain value. It is the same. It has that same relationship. And we know this because of the end behavior. If you were to take your graphing calculator and look at this, you would see that given the asymptote at positive 2, okay, we would have our horizontal asymptote at positive 3, and we would see our function up in the top right-hand corner and the bottom left-hand corner, okay? This is what our function would look like. Based on these characteristics, we know that end behavior, as x approaches positive 2, or 2 from the positive end, f of x approaches infinity, right? As we come in from the positive end, you can see your y values are increasing towards positive infinity. And as x approaches 2 from the negative end, f of x approaches negative infinity. So remember, your calculators are not going to show you the asymptotes. They're not necessarily going to be shown in there, but based off of the graph, you can visually identify those two lines and what the asymptotes are. All right, this next part, we're going to do it in two parts here. We're going to start by just looking at the function and seeing if we can identify the domain and the possible asymptotes. Okay, remember the domain comes from our h value, and even though this is not written in simple notation, we know that our denominator is not going to change, right? Even if we did the long division, our denominator stays the same, and based off of that, we can assume that our h value is positive 1, right? And given that it is positive 1, we could possibly have an asymptote at x equals 1. Now, we identifying the domain based off of the asymptote. I do understand it tells you to do it in interval notation. Remember, ignore the interval notation. We are focusing on set notation only. So the domain would be everything except for positive 1. Okay. If you take a look at the second function here, f of x equals x plus 5 times x minus 1, all divided by x plus 1, I do realize this is no longer a linear function. However, same rules apply. Our denominator is not going to change. Based off of the denominator, we know that we're going to have a possible asymptote at x equals negative 1, meaning our domain would be everything except for negative 1. Okay, and it's very easy to make that correlation. Asymptote defines your domain. You really should not have any struggles there. Okay, our third function, x minus 4 divided by x plus 1 times x minus 1. Now we do have two separate binomials here. So this tells me that we're going to have two separate asymptotes, right? In this case, x equals negative 1 and x equals positive 1. Remember, this is where we would apply zero product property in order to define those values for x. So because we have x equals negative 1 and x equals positive 1, that means we have two separate asymptotes. Okay, so yes, there can be more than one vertical asymptote in this case. Domain, we would define as x cannot equal -1 and x cannot equal +1. Simple enough. Okay, and our last function, 2x squared minus 3x minus 9 divided by x squared minus x minus 6. Now, our denominator is a quadratic function. We cannot have this as a quadratic function if we are to solve for x, so we do need to factor. Remember, factoring a quadratic, you can go ahead and use diamond method. Multiplies to -6, adds to -1. I know that those two factors are -3 and 2, right? -3 times 2 gives us -6, and -3 plus 2 gives us -1. So this can be changed into x minus 3 times x plus 2. Okay, and in doing so, again, apply zero product property. We have two vertical asymptotes at x equals 3 and x equals -2. For the domain, set notation defined for x cannot equal -2, and x cannot equal +3. Okay. Now, for the next part, it does say use a graphing calculator to graph each of the functions from step A and check to see if the vertical asymptotes occur where you expect. So here's what I want you to do. I want you to take your calculators and graph this. Okay. Now, let's go ahead and graph the first function together and sketch out that graph in our notes. All right, here's a quick refresher on how to graph. Remember, in order to graph, you're going to hit the y equals. In order to type in a fraction, you go alpha y equals 1. If your calculator does not have that graphing option or that fraction function, you're going to enter parentheses x plus 3, close parentheses, divided by parentheses x minus 1, close parentheses. Okay, now looking at the graph, I already have it pulled up. You can see that I have my two pieces here, right? But there's no asymptotes. Well, here's an easy way to determine where your asymptotes are located. You go second graph, and you're going to get a table of values. Now, how do we identify the asymptotes? Well, the vertical asymptote is easy to identify, and we can identify the vertical asymptote from the error. So you want to look for that error message for the y values. And it's giving us an error at x equals 1 because there are no points on the y when x is equal to 1, right? If I go back here and look, if I look at x equals 1, you can see that there's not going to be any y values because our function does not cross that point, meaning that our asymptote is located at x equals 1. For the horizontal asymptote, on your calculators, you will not be able to see this. All right, so as we just saw in our calculators, we can sketch out our graph, right, approximately, and this is what it looks like. You saw your coordinate plane, right, your x and y's, and as we talked about it, we know that we have a vertical asymptote at x equals 1. And then I told you guys that it is more difficult to determine where your horizontal asymptotes are from your calculator. It's not going to be given to you in the table of values. But here's what we did see. We saw part of our graph up here, and then we saw the other part of our graph approximately here, right? So we can go ahead and estimate our horizontal asymptote to be here. We don't know the location yet. That's okay. We're just sketching the graph. Okay, now I want you guys to go ahead and hit the pause button and go ahead and try the next two functions, graph these or make a sketch of these using your graphing calculators, and then come back and check your work. Here's what you should have for the second function. Okay, we confirmed the asymptote is at x equals -1 based on our calculator if you checked your table of values. And you can see that your graph does not have a horizontal asymptote, right? There's no point where I can draw a horizontal line splitting up the two pieces of our function. However, we could draw a line right in the middle of these going this direction. This here is called a slant asymptote. So we do have a third type of asymptote. We have vertical, horizontal, and now we have slant asymptotes. The third function, again, we confirm these asymptotes. We have one on the left, one on the right. We have three pieces to this function, the piece to the left, the center piece, and the piece to the right. Okay, so you can have more than two asymptotes. All right, and the last function here, we have our expression, okay, and we did factor and we did find the two horizontal asymptotes. Now, I want you to go ahead and graph this function. Take a minute and look at it. All right, you can see that I pulled up the graph here. I did this on Desmos just to show you guys what's going on here. So you can see that we do have a vertical asymptote at x equals -2, right? Our function approaches but does not cross that line. But we also had stated that we had a vertical asymptote at x equals 3. Well, if you look at the graph, there's no asymptote at x equals 3. Our function goes through that point. But now, if you go through and look at your table of values, okay, you can see here, let me type in 3, you can see that at 3, our y value is undefined. So what does that mean? When you have an undefined function like this or an undefined section, it creates what we call a hole because there is a value that should have an asymptote, but it doesn't have an asymptote. So when we sketch it out, okay, we have our asymptote at x equals -2, and then we do appear to have a horizontal asymptote. Okay, here's our horizontal asymptote. We can go ahead and sketch that out. We're assuming it's at what appeared to be +2. So we sketch our asymptotes, we draw our function, top left, and then on the bottom, when you sketch that second part, take into account the hole and you simply draw an open circle wherever there is a hole. Okay, and the only reason we do this is because, again, we assumed for there to be an asymptote where there was none, so we consider that to be a hole. Okay, so this here is not an asymptote. It is a hole. So for part B, now that we finished sketching these out, it says any unexpected results. And of course, no asymptote on that last example. Right? Instead, we have a hole. All right. Now, for your reflection question, it says rewrite 2x squared minus 3x minus 9 so that its numerator and denominator are factored. How does this form of the function explain the behavior of the function near x equals 3? Well, we already did the denominator, right? We factored it before we graphed it, and we know that the denominator is x minus 3, x plus 2. Now we just have to factor out the numerator. So looking at the numerator, let's go ahead and factor. And remember, we are doing diamond because it is a quadratic. Up top, we are taking a times c. So 2 times -9 gives us -18. B is -3. Two numbers that add up to negative, or that multiply to -18 but add to -3. -6 and +3. And then because our a value is greater than 1, right, this here, we divide our factors by a. And you can see we end up with x minus 3 times, bottoms up, times 2x plus 3. Okay, so the factored form of our function is f of x equals x minus 3 times 2x plus 3 divided by x plus 2 times x minus 3. Okay, and then it's asking us, can the behavior of the function be explained when you see it in factored form? And if you guys remember, back to module 9, anytime we had common factors in the numerator and denominator, they would cancel each other out, which simplifies into a function of 2x plus 3 over x plus 2. So our factor x minus 3 is where the whole is located in our graph. Okay. Now, if you're looking at this on your graphing calculator and you see, look at the table, right? At 3, so for this one, you can tell that you have a whole because where you look at x equals 3, you get an error message for the y value, just like we did for the asymptote. Okay. Let's talk a little bit more about the different asymptotes or discontinuities for wholes. A vertical asymptote occurs when a rational function has a factor in the denominator that is also or that is not also in the numerator. For example, x plus 6 divided by x minus 1 gives us a vertical asymptote at x equals 1 because remember, we solve for x. What we're doing here essentially is applying zero product property and solving for x in the denominator. That is how we arrive at the conclusion that x equals 1. When we have a whole, it occurs when a rational function has a factor in the denominator that is also in the numerator. So this would be examples where we can cancel out, right, those common factors, and that's what would create our wholes. Now, you can see this example here is stated. We have a whole at 3, and the exact location is 3, 5. And the way we determine the location of this whole is by taking the value of x for which we solved, right? This came from the denominator. And because we cancel out, we simply solve by substituting it into the function. Our function now is f of x equals x plus 2. And if we were to substitute 3 for x, we get 3 plus 2. And we know that when x is 3, y is 5. So our location, the whole location, is at 3, 5. Okay. Now, following example says to state the domain of the following and determine if the graph has a vertical asymptote or whole at that x value. For A, we have x minus 6 over x plus 2. It's already simplified to linear terms. You can see that we cannot cancel anything out. So based on the denominator, we can say that we have a vertical asymptote at x equals negative 2. Remember, we solve for x, and that's the location of our asymptote. The domain in set notation, remember we're sticking to set notation, use curly brackets. We have x defined for everything except for negative 2. Okay, now hit the pause button, factor the function of b, and determine your vertical asymptotes or wholes. You should have factored it into x plus 2 times x plus 1 over x minus 3 times x plus 1. And of course, because they have that common factor, x plus 1 cancels out, which means that we have a vertical asymptote at x equals 3. And then because we also had the factor of x plus 1 in the denominator and it got canceled out, it created a whole. So we do have a whole at x equals negative 1. For the domain, there's no difference. We simply state both of those excluded values in the set notation.